This video is about capacitors. It corresponds to section 10.1, or the first part of section 10.1 of Applied Analog Electronics. What is a capacitor exactly? It's the second sort of component that we'll be looking at in this course. The first type of component was the resistor, and we looked at resistors that were fixed resistors, and we looked at resistors that were sensors, whose resistance changed depending on a physical property we were trying to measure. It's the same way with capacitors. We'll be looking at fixed capacitors and at capacitors that are sensors, whose capacitance varies depending on the physical property we're trying to measure. Now, a capacitor itself is a fairly simple device. It consists of two conductors separated by an insulator. And the way this is drawn in a schematic diagram is with two plates parallel to each other that are the two conductors, and wires come in to connect to those two conductors, and then a gap between them that corresponds to the insulator. Now, the basic fundamental phenomenon here is that we have an insulator. So we cannot take electrons and push them through from one side to the other. They don't go through the insulator. So what happens if we do try to push electrons into this thing? Well, they basically accumulate on the plate, giving you a charge. And that charge results in a voltage difference between these two plates of the capacitor. So you can think of it as either we put an electric field there and that gives us a charge, or we can put a charge there and that gives us an electric field. The two concepts are sort of interchangeable. There is a relationship between the charge, which we symbolize with Q, and the voltage. They're proportional to each other. And this constant proportionality is called the capacitance. So this is charge, this is voltage, and the product of the capacitance and the voltage is the charge. Now, it helps sometimes to look at sort of physical analogies that are easier to understand, and the hydraulic analogy is the most popular one for electronics. And for that one, we'll come up with two. One of them is for a capacitor where one side is connected to ground, and we have this other node that we can connect to, and we can put charge in, take charge out. Or, if you think of it another way, we can apply a voltage here, and charge will accumulate or not on the capacitor. Okay, the physical hydraulic analogy of that is to think of having a large cylindrical tank with a pipe connected to it at the bottom. The charge corresponds to the amount of water in the tank. Okay, so if we've got a certain level of water in the tank, well, how much voltage do we have? Well, voltage corresponds to pressure in the hydraulic analogy, and the pressure is going to depend on how high this is. So voltage corresponds to height. All right, what about charge? Well, the charge corresponds to how much total volume we have, which is Q then corresponds to the height times the area of the cross-sectional area of this tank. That's the volume of water. So we've got this analogy here where voltage corresponds to the height of the water in the tank, the charge corresponds to the total amount of water, and the capacitance corresponds to the cross-sectional area of the tank. If you have a very large tank, it takes a lot of water to fill it up even just a little ways. So a lot of charge needed to get even a small change in voltage if you have a very large capacitance. If you have a very small capacitance, then small amounts of charge will give you large changes in voltage, because you have a very skinny tank where just small amounts of water shoot the level way up. Okay, that's a nice analogy for a capacitor where we've got one side tied to a constant. if both ends of the capacitor are accessible, if you've got either end can change its voltage, so we've got something that looks like this. Can we come up with an analogy for that one also? We can, but it's not quite as intuitive. What we end up with doing is taking a large cylindrical pipe and sticking a piston in it. So this piston fits tightly in the cylinder so that you can't have water flowing through the piston. You push the water in here, it's going to move the piston, but it's not going to flow through. So corresponds to our insulator. Now, to get the effect of this pressure relationship to volume, or voltage relationship to charge, we're going to put some springs on this piston so that the more you displace it from its rest position, the more force you have on the springs. A nice linear relationship between how much you displace the piston and how much force is on the spring. Well, that force on the spring gets converted into how much pressure is there on this piston. And so we're going to again get the amount of displacement here times the area of the piston gives you the volume, and the force is going to be proportional to, or the pressure is going to be proportional to the displacement. And so again we have something where the voltage now corresponds to how much have we pushed this piston. That's how much pressure do we have on the water. And the charge is going to correspond to how much volume of water did it take to get that effect. And again, we're going to have a rough correspondence with capacitance being corresponding roughly to the area of the piston. Though the analogy isn't quite as good here because we have to take this spring constant into effect, and we're interested in pressure rather than force. So this analogy takes a little more care to work it out, to get things that are numerically corresponding and not just sort of intuitively similar. But the basic idea here, that water doesn't flow through, but if I push water in and take water out, so if I have an oscillating pressure here, well, the piston is going to move back and forth, and I'll get an oscillating pressure coming out the other side. So I can still get information flow through here. I can still get movement of water. It doesn't go all the way through. It's not a direct current, but I can get movement of water that is starting on one side, coming out the other side. And we'll have the same effect with capacitors. We won't be able to get a DC current through them, but if we put an alternating voltage on one side, we'll get an alternating voltage coming out the other side. And that's, in fact, a large chunk of what capacitors is used for, is that phenomenon. Let's take a look at this thing a little bit more mathematically. How can we, for instance, estimate the capacitance of a capacitor? We've got two conductors, we've got an insulator. Is there something physical about that we can use to estimate its capacitance? And it turns out, yes. We can estimate the capacitance with just a few different parameters. And these are some constants. One of them is K, which is the relative dielectric constant, and it is determined by what material we use for the insulator. If we use air or vacuum, it's a 1. If we use just about anything else, it's bigger. Plastics are usually around 2 or 2.5. Then we have a physical constant called epsilon naught. It is the permittivity of free space, and epsilon naught is about 8.85 picofarads per meter. Then, okay, so this is just talking about the dielectric constant and property of the universe. We need to have something that's specific to the particular capacitor we're looking at. And basically the capacitance goes up with the area of the plates here, the two conductors, and it goes inversely proportional to the distance between them. So if we put them very close together, we have a large capacitance. If we move them very far apart, we have a small capacitance. If we make them to be very big conductors, we have a large capacitance. If we make the conductors very small, we have a small capacitance. And this formula will turn out to be important for the touch sensor that you're going to be making, because you will need to estimate how much capacitance you're going to get from a finger touch. And that's going to depend on what you're touching, the material of the dielectric, how much area you're covering, and how thick the material is that you're touching. So that's a formula we're going to need. It's not the only mathematical formula, though, that we're interested in with capacitors. Usually when we're dealing with electronics, we're not looking directly at charge. We're usually looking at current. Current is the movement of charge, and if you're looking at a circuit like the capacitor with one side tied to a constant voltage, if we put current in here, it's going to accumulate on this capacitor since it hasn't got anywhere to go, and the charge will increase. If we take current out, the charge will decrease. The charge is basically the integral of the current, or turning it the other way around, the current is the derivative of the charge, derivative with respect to time. But we already had another formula that says that Q equals CV. We can put these two together. Just use the multiplication rule. I is equal to dc dt v plus dv dt c. Now, this formula is good mathematics, and we will be using it at times in the class. But if you look in electronics books, they usually write it a little bit differently. They write I equals C dv dt. So they're using just the second term here. What happened to this first term? Well, what they're talking about are fixed capacitors. If the capacitance doesn't change, then dc dt, the change of capacitance with respect to time, is 0. And that term disappears. So there's a lot of times when we can get away with using this simpler form, I equals C dv dt. But it's not quite right. And when we're looking at capacitance-based sensors, where what we're looking at, what the signal we're interested in, is the changing capacitance, then this part of the formula starts mattering. So be aware that there are times when you can think about everything in terms of just as a constant capacitance. I equals C dv dt, everything works fine. So I is a function of time, V is a function of time, but C is not. C is a constant here. But if C is a function of time, then you can't ignore this other term. Okay, that's probably enough of the basic math for now. We'll do another video in which we look at capacitors and look at the impedance of capacitors, which calls for a video all by itself.